Hello everyone, my name is Erica Jensen and I'm a student at the University of Colorado Boulder. My co-authors are Professor Shudong Chen and Professor Daniel Shears, and I'll be talking about optimal spacecraft guidance with asynchronous measurements and noisy impulsive controls. The goal of this work will be to design an optimal guidance law to minimize the mean squared deviation of a stochastic system state about some target state. We would like the guidance law to be computationally efficient to enable onboard implementation, and we also desire neighboring guidance, or in other words, a guidance law that operates in the linear region about some nominal nonlinear spacecraft trajectory. In our system model, we consider linear time-varying dynamics, additive and control linear noise, impulsive controls, and sampled measurement outputs. The sampled measurement assumption is more realistic for spacecraft that don't have continuous access to new measurements. By control linear noise, I'm referring to noise that is linearly proportional to the control magnitude. And experimental studies have shown that electric propulsion engines experience discharge current fluctuations that are linearly proportional to the level of nominal thrust. The Gates model for maneuver execution errors also incorporates fixed and proportional delta V errors. So in short, higher thrust produces larger errors, and we would like to account for that in our optimization. However, control linear noise is often neglected in spacecraft mission design due to its increased complexity. Some relevant work has been done in the area of feedback stabilization with control-dependent noise. And by feedback stabilization, I refer to problems where we minimize cost functions that are quadratic in the state and the control with the goal of stabilizing the system about the origin. This is similar to an LQG augmented with control-dependent noise. A similar problem is that of stochastic reachability with control-dependent noise. And in the realm of spacecraft guidance, authors have developed robust guidance methods based on stochastic chance constraints. However, these methods do not explicitly accommodate control-dependent noise. These authors have also assumed the case of continuous measurements, or state information that's available at all times along the trajectory. And we're really more interested in the case of sampled measurements, which we have addressed in our previous work, but with some limitations. For example, our previous work did not account for pointing errors and did not include additive noise. In this presentation, we'll expand on our previous work and contribute an analytical solution to the optimal control problem. We'll show that the controls are linear in the measurements and the target state, and that feedback gains can be computed offline. We'll also present some numerical studies to demonstrate the performance of the optimal control. Now, moving on to the problem formulation, we'll consider the following state dynamics, where WT is a standard Wiener process driving the additive noise. And we'll consider a total of n perfect full state measurements that will be scheduled a priori. The measurement times serve to discretize the trajectory into segments, and we'll refer to the segment between the measurement at time tk and the measurement at time tk plus 1 as segment k. The perfect full state measurement assumption is important for the analytical optimization performed in this presentation, and I'll talk more about that later on. During segment K, we will include a total of pk impulsive control inputs, which will create discrete state updates along the trajectory. Here, delta U is our nominal control impulse, and E sub I are independent random variables that dictate the control linear noise. And here we have an arbitrary number of control linear noise sources. Our goal is to find the optimal impulsive controls that minimize this cost function, where the first term in the cost function is the mean squared deviation about the target state, which is denoted x hat f, and the second term is a control penalty term. The matrix R is required to be positive definite in general as a regularization condition. However, this condition can be relaxed in some cases, and I'll discuss that in the coming slides. We'll assume that the initial state is known but arbitrary, or we can consider that the initial state is another perfect full state measurement. Now we'll present the result of this optimization as a main theorem, which states that the optimal impulsive controls are linear in the previous measurement ytk and the target state x hat f. We also find that the minimized cost function is quadratic in the initial state and the target state. The gain matrices K and L and these other relevant quantities can all be computed offline a priori through recursive equations. These recursive equations are incorporated in this algorithm shown on the left, and in the process of applying this optimal control, we would compute these quantities offline beforehand, and then in real time, our optimal control would be linear in the measurements and the target state. We find that the control penalty matrix R can be positive semi-definite if this matrix here is invertible, which is typically the case in spacecraft guidance. And we can also prove that other matrix inverses in this algorithm are guaranteed to exist. Moving on to the proof of the main theorem, we will use dynamic programming or solve the Bellman equation, and we define a value function from measurement time tk to the final time tf. This value function takes the inputs of the state at time tk, the target state x hat f, and the controls over the period, and we'll optimize the problem backwards in time using dynamic programming, beginning with the final segment of the trajectory from measurement time tn to the final time tf. First, I'll note that we can express the mean state and the covariance between impulsive control updates with these two equations. The impulsive controls will create discontinuities in the mean state and the covariance, which are described by these two equations here. Collectively, this gives us the information we need to compute analytically the covariance in the mean state over this entire segment from the measurement at time tn to the final time tf. Then we can do a bias variance decomposition to express the mean squared deviation in terms of the state covariance and the mean state at the final time. We can substitute this expression in our value function v sub n, and we find that the value function is quadratic in the controls that we're trying to optimize. So we simply need to do a first order analysis or satisfy this necessary condition to optimize the controls. And at the end of this process, we find that the optimal value function is quadratic in the measurement at time tn and the target state x hat f. These matrices, w, c, and f, can be computed offline using algorithm 1. Following our dynamic programming approach, we can proceed backwards in time and optimize the value function from segment tn-1 to the final time tf. And from Bellman's principle of optimality, we can express the value function in terms of v sub n, the value function that we've previously optimized. In doing so, we find that the value function vn-1 remains quadratic in the controls, and we can repeat our first order analysis. We also find that a recursive form quickly emerges for the optimal controls and the optimal value function. Now we'll talk about the implementation of this linear guidance law as neighboring guidance about a nonlinear trajectory. We can begin by considering some nonlinear stochastic dynamics as well as some nominal nonlinear dynamics, and we want to control the deviations of the stochastic state from the nominal state, which is described here by this equation. We'll approximate these state deviations by the first order term or linear term in a Taylor series expansion, and the partial derivatives here will be evaluated along the nominal trajectory, so they are deterministic. Now we can apply this guidance law to Sun terminator orbits at the asteroid Bennu, and this will be a 24-hour simulation. Our nominal dynamics will be described in a rotating coordinate frame with point mass gravity and solar radiation pressure. In our stochastic dynamics, we'll include additive noise to account for dynamical mismodeling about each axis. And we'll also include another additive noise process along the x-axis to account for uncertainty in solar radiation pressure. We'll also include control linear magnitude and pointing errors along each axis. Here we're showing some sample results for a case where we have evenly spaced measurements and controls along the trajectory. On the left, we have 3 measurements and 6 impulses per segment, and on the right, we have 25 impulses per segment. In any case, these trajectories are generated as sample paths of the nonlinear stochastic dynamics. The blue trajectories show the performance without active guidance, and the red trajectories show the performance with the optimal guidance law. We can see that although the spacecraft starts off with a relatively large initial state error, the spacecraft state is steered relatively close to the nominal trajectory. We can also do some numerical studies to see how the guidance performs as we increase the number of measurements and controls. And we find that the optimal cost appears to decay to a positive limiting value as we increase the number of measurements and the number of controls to infinity. In conclusion, we have considered linear time varying systems with additive and control linear noise, impulsive controls, and sampled measurements. And we've derived an optimal guidance law to minimize the mean squared deviation of a stochastic system state about some target state. The optimal control is linear in the measurements and the target state, and the gain matrices can be computed offline. We've also shown that the mean squared deviation decays asymptotically as we increase the number of measurements and controls. In the future work, we are interested in relaxing the perfect full state measurement assumption and including noisy partial state measurements. However, this problem is much more complex because we find that this destroys the separation principle between control and estimation. And the problem is no longer Markovian in the sense that the optimal controls don't simply depend on the previous measurement, but they depend on all past measurements and are likely nonlinear in those measurements. We're also interested in the problem of optimal measurement and control scheduling. Thank you for watching, and if you have any questions, please feel free to contact me at this email address listed below.